All right, let's get started. Good morning, guys, and good morning, Mr. Banana. So the midterm grade is already out. I think in general you did pretty well, but I hope some of you have done better. I'll talk more about the grades and then something about that midterm survey tomorrow when that is due. So today we're going to just move on to the next topic, which is about combinational minimization using a more computer-friendly algorithm called Quine-McCluskey algorithm. And this algorithm has two components. One of them is called tabulation method. That is called minimization with a particular chart. And after that, there are certain scenarios where this new algorithm cannot solve, and then we also have a new solution for that, which is called Petrick's method. All right, since we're going to study Quine-McCluskey algorithm, so here's Dr. Quine and Dr. McCluskey. So Dr. McCluskey is really a pioneer in the field of electrical engineering. For those of you in the CE major, have you heard about this guy? The other courses? No. So he has developed many things. For one, this combinational minimization algorithm, and also he's the pioneer in sequential modeling. Like this idea of finite state machine was partly contributed by Dr. McCluskey. He also developed the idea of hazard, which is a reliability issue for integrated circuits. So he's really the guy that has a lot of contributions in the field of electrical engineering. Dr. Quine is more like a mathematician and philosopher. He doesn't have much work in circuit design, but this is one thing that he, together with McCluskey, developed an algorithm. So this is actually the first algorithm developed for minimizing combinational circuits. This is even before K-maps. And functionally, it is identical to K-map. We use K-map to find prime impedance and eventually find the minimum covered. Quine-McCluskey algorithm is really doing the very same thing. But this is capable of handling a lot more variables. For K-map, you can do 4 variables pretty comfortably with edge wraparound, corner wraparound, top and bottom wraparound. With 5 variables, you could do that. The book has one way of doing it. With 6 variables, you can also sort of create a diagonal K-map going in 2 different directions, creating 2 K-maps, put them side by side, that sort of stuff. But you can hardly go more than 6 variables. That's one of the benefits of this algorithm. This can handle any number of variables with ease. And this is also more efficient in a computer algorithm. K-map is good for visualization. This algorithm is better as a computer algorithm. All right. And Dr. McCluskey, without any surprise, has also worked at Bell Labs when Carnot and Hamming were also at that place. And this is a timeline of their major contribution. So Hamming developed the idea of Hamming distance at 1952. And a few years later, Quine and Carnot, they developed their own logic minimization algorithm. And actually, McCluskey developed the algorithm when he was still a PhD student at MIT, and later he worked at Princeton, and then Bell Labs, and later moved to Stanford. All right, so this is a motivational example for a logic minimization algorithm. You can do logic minimization using Boolean algebra by grouping together these adjacent minterms, and K-map just provides a better visualization. And in general, to do simplification with K-map, we follow these steps. We first find out the prime impedance. These are the candidates that could go into the minimal expression. We then pick the essential prime impedance. These are the things that you must include in the final expression. And finally, once we pick the essential prime impedance, we just have to cover the remaining minterms with the fewest impedance. And at that point, it's pretty much a heuristic algorithm with K-map. By visually seeing the relationship, see which impedance cover which minterm, and find the best way to cover the remaining. All right, and in this example, I have this. This is one of my essential prime impedance. This is another of my essential prime impedance. And once I included the 2 essential ones, I just have to cover the remaining minterms with the best set of impedance, which is that single impedance in this case. So as I said, Quine-McCluskey algorithm is functionally equivalent to K-map. So it roughly follows the same procedure. In the Quine-McCluskey algorithm, you still first find out the prime impedance by using a different method called tabulation method. And then we solve for that cover problem to cover all the ones with the fewest impedance using prime impedance chart. And in certain scenarios, this algorithm just couldn't do any brute force or greedy pruning. At that point, there's a backup method called Petrick's method, which we'll get to at the end of the lecture. So here's a general idea of the tabulation method, starting with a K-map. Well, again, K-map and tabulation method, or K-map and Quine-McCluskey method, are functionally equivalent. So most of this analysis can also be done with the help of K-map. So let's try a four-variable example and see how this process works for K-map and also for the Quine-McCluskey, the tabulation method. So the idea, the first step in this logic minimization algorithm is to find out the prime implicants. For us to do that from K-map, I tend to start with some larger implicants. I'll try to find this group of four, and try to find prime implicants for the remaining minterms. But computer algorithm, again, works in a different way. Right? Human intuition and computer algorithms are often different. For this algorithm to work, it has to start small. Start with the inputs, which are the set of minterms given to the algorithm, and try to construct larger and larger implicants until it finds out the prime implicants. The starting point of tabulation method is with a set of inputs, and they will just try to combine every adjacent pair of minterms into a 2-minterm implicant. And as you can see, there are many 2-minterm implicants over there, right, which are not prime yet. So we have this. This is one implicant. This is another one, right? And I will just. This is another 2-minterm implicant, 2-minterm, the wraparound 2-minterm. And I think those are pretty much all the 2-minterm implicants. Right? You have a few going in the horizontal direction, a few going in the vertical direction. Right? Okay. And then with these 2-minterm implicants, what we can do is we can combine some of them into even bigger implicants. Right? So let's say these two can be combined into a bigger implicant like this. Right? These two can be combined into that whole column, which is a bigger implicant. And we just keep doing this combination until we cannot grow them any further. At that point, we have all the prime implicants. Right. So for K-map, you tend to go directly to 4-minterm implicants. But for computer algorithm, they have to start small, start with the input information, which are all the minterms, and then gradually construct bigger and bigger implicants. Yeah. Any questions so far? Here's just a better picture of what I just did. I have a bunch of 2-minterm implicants. Right? Many of them are not prime yet, but some of them can be combined further into bigger implicants. And at the end of the day, in this example, you get up to 4-minterm implicants. You could have an 8-minterm implicants, 16, 32-minterm implicants. And you can just keep doing this process until you get all the prime implicants. Right? You get all the implicants that cannot be grown any further. So seeing that, I have a question for you. How would you implement this algorithm? Right, let's say I give you a list of minterms. Minterm 0, 1, 2, 3, 4, 5, 8, 9, 10, 11. I give you a list of minterms. How would you write a computer algorithm for this algorithm? Right? How would you implement this in your favorite programming language? Right, in particular, how do you store this information and how do you process them? In what kind of algorithm, what kind of operations? I'll give you half a minute to think about this question. And then here's some of your inputs. All right. Any ideas? Any idea you want to share with us? Yeah. A directed graph. Could you be more specific? Like, how do you construct the graph and how do you process the graph? I see. So you treat each minterm as a node in the graph, and then you sort of convert those green circles into like a graph. and also representing the adjacency relationship. Right? So let's see. Think about those, green circles, green squares as nodes in a graph, and then we can sort of like add some edges indicating which one are adjacent. Right? And then you'll just probably traverse through the graph and then find all the adjacent nodes and then represent that as a larger node, right? Which is a 2 min-term implicant. And you can keep doing this among like another graph for a bunch of 2 min-term nodes, and then further check their adjacency and then grow it even further. That's very nice. But another question is, if you do that, how do you identify these neighbors? Okay, the starting point is a bunch of indices, right? Min-term 0, 1, 2, 3. This is min-term 4, min-term 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Those are the min-term indices. How did you check for adjacency from those integers? Right, to really construct the graph. Yeah, anyone has some different ideas? I also like to hear from other people in the class. Again, for this question, like given indices, how do you determine their adjacency? Right, so let's say 4 and 12, they're adjacent. Right, and how would you determine that? If I give you these two numbers, yeah, how do you determine that? A bitwise operation. I think that's a good idea. If I write them in binary, right, it's 40100, 12 is 1100. Adjacency relationship is a little bit more obvious. Right? They differ by 1 bit. They have a Hamming distance of 1, so they're adjacent. If you can somehow represent these indices in binary as a binary vector, you can do some bitwise manipulation and then essentially count the number of ones in the resulting binary string. Right? Maybe you could send them through let's say an XOR function, a bitwise XOR. Right? Then you will figure out that they differ at 1000. Essentially, they only differ on the leftmost position. And you somehow count the number of ones in this resulting binary vector. And if it's 1, they're adjacent. Right? The idea is this Hamming adjacency is really a binary relationship between two binary strings. So in computer algorithm, we probably want to represent them as a binary string and then do all the adjacency checking based on this binary string. But we would also need something like a graph or a table to record all these processing that we have done. So binary manipulation together with some kind of data structure, graph, table, should be sufficient to implement this algorithm. Right? See, in the implementation of this algorithm, I don't have to care too much about their position in the K-map. Like I can sort of do manipulation with binary numbers. That is the beauty of the Quine-McCluskey algorithm, a way to handle larger number of more variables without the visual aid by just manipulating on their binary representation. All right. So for one thing, and the other thing is at the high-level control algorithm, you want to check for which one is a neighbor with which, right? So whether 4 and 12 are neighbors, whether 4 and 15 are neighbors. Again, without the visual aid, you probably have to do all those pairwise comparisons. And that could be a lot of work. And some of those work actually a little bit meaningless. 4 and 15, they just differ by too many bits. If you can somehow identify that information early on and then do some pruning to reduce a problem to a smaller problem, you can probably develop a much more efficient algorithm. So we talk about 3 questions. Number 1, how to represent these numbers. We decided to represent them in binary. And number 2, how to manipulate them, probably through an XOR, and then find how many ones do I have in this bitwise XOR string. And also at a high level, how do I remember these comparison results, maybe in a graph or in a table. And also, when we're doing the pairwise comparison, we probably need to optimize that algorithm a bit further. All right. So with that, I'm going to show you something about just in general, how do we develop an algorithm. All right, I'm going to switch to my camera. All right, so I have some, playing cards. Just going to random sample some of the cards from the stack. And let's say these are the, oh, it's probably too many. These are the cards I have. Right. Okay, all right. So I have a bunch of cards. I'm going to treat queen as 12, right? So they represent a bunch of integers. So suppose I want you to find all the pairs that add up to an even number, right? The first algorithm you can try is to compare all the pairs, which will definitely give you the correct result. But it's a little bit, too much work, right? You'll probably do some sorting before you run that algorithm. And how would you sort? Yes. Yeah, you put odd cards on one side, even cards on the other side. Right? So let's say I put all the cards over here. These are odd numbers. Those are even numbers. Right? Again, queen is 12. So those are even numbers. And then I ask you to find all the pairs that add up to an even number. It's going to be 2 cards from this side. So 3 choose 2 plus 2 cards on this side. 6 choose 2. And that gives you all the combinations. You're doing much fewer comparisons compared to just blending them in and then checking out the pairs. Right? So let's say I give you a different task. Find all the pairs that add up to a multiple of 3. So essentially 0 mod 3. Right? How would you sort the cards? Yeah. Yeah. So let's say everything that is divisible by 3, so 6 and 12, those are divisible by 3. What about the remaining cards? And 3 is also divisible by 3. All right, this is a good starting point. And with this, I think you have essentially 2 categories of methods to have 2 cards adding up to a multiple of 3. Any 2 cards from this side. Right? So 4 choose 3. And within this pack, you have to do a more detailed comparison. Right? Every pair you compare, compare, compare. You can probably do a bit of further sorting. So this is essentially the pack of 0 mod 3. You can have another pack for 1 mod 3, another pack for 2 mod 3. So 3n plus 0, 3n plus 1, 3n plus 2. So let's say if we do that sorting. So these are like 3n plus 1, 3n plus 1, 3n plus 2. Right? Different kind of sorting. And with this, again, any 2 cards from this set add up to a multiple of 3. Any combination, 1 from this pack and 1 from this pack, will also add up to a multiple of 3. And those are all the possibilities. You see, what I'm doing here is, depending on the job, I do sorting differently. And different sorting, the best sorting will give me a very easy algorithm because I get rid of a lot of the unnecessary work. By just going through these cards in a linear fashion at the beginning, and then put them in different buckets, and then combine this bucket in different ways, you can get rid of a lot of the unnecessary comparisons. All right. So that's really the same idea when we come back to this Quine-McCluskey algorithm. We want to check for all the adjacent minterms, but without the visual aids, you can do all the pairwise comparison, which is a lot of work, or you can do some sorting first to eliminate the unnecessary work and only give yourself a much smaller question to deal with. All right. So this is essentially the idea of bucket sort. So bucket sort is usually a pre-processing step. Before you actually run some algorithm, you first do some sorting, do some categorization to simplify the problem. All right. And we can use it as a pre-processing step before we do the Hamming distance comparison for those indices, for those binary numbers. All right. So again, the starting point of this algorithm is a bunch of minterms. And our goal is to find all the adjacent minterms to get 2 minterm implicants, and 4 and 8 and larger implicants. Right. So those numbers, those indices, can be represented in binary to make comparison easier. We can do sorting based on the number of ones. We have 1 minterm that contains no 1, so that's put in the bucket 0. Right? We have a few minterms, 0001, 1000, and 0010. They have only a single 1. We put them in a different bucket. Right? 2 ones, 3 ones, and 4 ones. We don't have all ones, so the 4 ones bucket is empty. Right? And once you have put minterms in these buckets, elements in non-adjacent buckets are never Hamming adjacent because they have different numbers of ones. So for example, between bucket 0 and bucket 2, they have different number of ones, right? 0, 1, 2 ones. So they can never be hemi-adjacent. In the best case, they're hemi-distance 2 away. Right? Similarly, between bucket 1 and bucket 3, they differ by at least 2 bits, right? Sometimes even more. So if you look at 0001 with 0111, they differ by 2 bits in the middle. If you look at 0001 and 1110, they actually differ by 4 bits. But between bucket 1 and bucket 3, they differ by at least 2 bits, which means they can never be hemi-adjacent. And therefore, there's no point in making comparison between those elements. Within adjacent buckets, they could be hemi-adjacent, not necessarily. Right? We haven't really do the full pruning. We have done a lot of pruning, but since in the adjacent buckets, they sometimes are hemi-adjacent, like everything from here with here, they're always hemi-adjacent. But between bucket 1 and bucket 2, they are only sometimes hemi-adjacent. So within every adjacent bucket, you have to do some additional comparison. But that's already a lot better than doing all the pairwise comparisons. So let's say between 0 and 1, they are adjacent. Right? So those can be combined into a larger 2 min-term implicant. Between bucket 1 and bucket 2, they are adjacent. These two are not adjacent. These two are not adjacent. Right? They actually differ by 3 bits. And the next one, I'm going to compare it with 1001, which are also adjacent. And finally, that element with every element, with the fourth element, 1010. Again, they differ by 3 bits, so they're not adjacent. Right? You only need to do comparison within adjacent buckets. All right. So again, since we're just dealing with 4 variables, we can also have the same visualization in a K-map. But remember, generally this is not available when you deal with a larger function. Right? But to get us started, the very same hemi-adjacency can also be visually seen from the K-map. So I just mentioned that all of these things from bucket 0 and bucket 1, they're always equivalent. And indeed, you have 3 implicants involving the 0 min-term, right? The 0000 min-term 0 in this K-map. Right? So let's say between 001, it's adjacent to these 2 elements only. Right? So I'm going to locate 0001, 0001. And for one thing can be combined with that group 0 element, but also you have these 2 implicants, this one, and the other wraparound. Those are the 2 additional implicants. By combining a min-term from, with only a single one, and this min-term has 2 ones, this min-term has 2 ones in its binary representation. Those are some additional 2 min-term implicants you can get by combining bucket 1 and bucket 2. And I also show that on the top right corner, that's the number of min-terms, the number of ones for each min-term. Top left corner, 000 has 0, 1. This center cell, 1111, has 4 ones. And then we move up and down, left and right by 1 position. The number of ones differ by 1. Right? So you have all the 3 1 min-terms sitting next to 4, all the single 1 min-terms sitting next to 0. Right? And this table at the bottom, the K-map is also color-coded to match the number of ones. Any questions so far? Questions? All right. All right. So formally speaking, this is how we do tabulation method. Again, tabulation method is step 1 in the Quine-McCluskey algorithm to find all the prime implicants by grouping together min-terms into implicants and smaller implicants into bigger implicants. So formally, we show them in this table, and we sort min-terms in different groups. So each group is essentially one of my buckets. Group 0 with 0, 1, group 1 with a single 1, group 2 with 2 ones, group 3 with 3 ones. Right? So a group is a bucket. And we have different columns. So in the first column, you just put down all the min-terms. And in column 2, it's probably some combination result from 2 min-terms, which are 2 min-term implicants. Next column, you have bigger implicants with 4 min-terms. Next column, you have even bigger implicants with 8 minterms. Just keep running this combining and uniting algorithm until you cannot unite them any further. All right. And there's also a little box next to each binary representation. Right? And this is used to record prime implicants. Right? If one of the minterm has been used to combine with another minterm to create a bigger implicants, we're going to put a check mark next to those two minterms, indicating that they are no longer prime implicants. Just because they have been combined into a bigger one, so that bigger one is definitely more prime compared to the initial minterms. All right, and we're going to have these columns, several columns, and in each column we're going to have a lot of those little boxes. All right. So to construct bigger implicants, you check for adjacent groups and then compare their binary numbers. And whenever the binary number differ by 1 bit, they can be combined into a larger implicant. And whenever things get combined, we use a dash to indicate the variable that have disappeared. So for example, 0000 and 001, those are these two minterms. They can be combined into a larger implicant. And therefore, they're shown as 000 dash. The variable that those two minterms disagree on will essentially be eliminated. You can see that pretty well from the K-map. In the K-map, if I combine them, I would have got the prime implicant of A prime, or not a prime implicant, an implicant, A prime, B prime, C prime, which is essentially saying 000 on the ABC variable, and variable D disappears. So dash really means that variable disappears in a product representation. Right. You can also see, again, the very same relationship through Boolean algebra. You have A prime, B prime, C prime, D prime, plus A prime, B prime, C prime, D, which by the uniting theorem, or distributivity together with complement, you get A prime, B prime, C prime. Again, variable D disappears. So we represent that as a little dash. Right. And whenever we do this combination, we're going to put a check mark at these two minterms, indicating that they are no longer prime, because I already found a larger implicant to cover those minterms. That doesn't mean you cannot use those minterms to combine with other minterms. You can still use the same minterm, let's say minterm 0, to combine with another minterm. These implicants could overlap. Actually, you have 3 two-minterm implicants overlapping on position 0. So you can use 0 to combine with minterm number 2 to get, okay, I'm going to do some color coding. Minterm number 2 to get the second two-minterm implicant. You can combine minterm 0 with the next minterm to create another implicant. You can use each minterm multiple times. But whenever you use it, at least once, you put down a check mark indicating that it's no longer prime. All right. So in fact, between group 0 and group 1, you can always do this combination. Because there's only one possible element in group 0, the all 0 representation. And whenever you have another representation with a single one, they definitely differ by only 1 bit. That's like a special property of group 0. Between group 1 and group 2, you have to really do the comparison, because some of them cannot be combined. Again, this sorting is only an initial pre-processing step. It doesn't give you all the information. Right. So maybe let's move on to the next set of groups, group 1, group 2. And we're just going to check for each minterm in group 1, can it be combined with some other elements in group 2? So 0001 and 0101, they differ only on the second bit. So the variable B disappears. You have 0-01. This one together with 1001, they differ only on the leftmost bit. So that becomes a dash 001. Right. And then nothing more with 0001. Then move on to the second element in group 1 and then compare it with each and every element in group 2 to check for their adjacency. 0010 combined with 0110 gives you 0-10. Right. 0010 with the last one over here. Right. They only differ on the leftmost bit, so dash 010. You see, it is quite a bit of work. Still a lot of comparison. Better than all the pairs, but still some work. And finally, 1001. I'll switch my color a little bit. 1001, 1001. It's a hemi-adjacent with those two elements in group 2, which gives you these two elements in the second column by getting rid of the kind of diverging variable. And as you can see, in this combination, we actually used all the minterms in group 2. So make sure to put down a check mark for each of those minterms, indicating that they are non-prime. All right. And similarly, you can do the same thing for group 2 and group 3. Check out the pairs, compare hemi-adjacency, and then mark things as combined by putting down a little check mark. I think in this example, you actually get to put down a check mark for all the elements in the first column. All right. And then we just keep doing it for the second column, combine two elements from the second column into the third column. And again, in the second column, we actually also only care about adjacent groups. So again, column 2 is divided into, in this case, 3 groups. This group is sort of like group 0 and 1 combined. This group is like group 1 and 2 combined. The last group is, you can call that group 2 and 3 combined. Everything in the top group will only have a single, have no ones. Everything in this group has a single one. Everything in this group has 2 ones. So between the top and bottom group, they are at least hemi-distance 2 away, so they can never be neighbors. Right. So let's compare again within adjacent groups, if there's anything that differ by only 1 bit. Right. So let's say 0, 0, 0 dash. I just have to quickly run through all the other elements. I do find this one. 1, 0, 0 dash. They differ only on the leftmost position. So that gives you dash 0, 0 dash. Okay, in terms of Boolean algebra, this is what I'm doing. I'm combining A prime, B prime, C prime with A, B prime, C prime into B prime, C prime without variable A and without variable D. So both of those variables become dash. All right. Or in terms of K-map, let's see what is happening. 0, 0, 0 dash. That's this implicant. 1, 0, 0 dash, 1, 0, 0 for ABC is this implicant. These two are indeed neighbors, right? They can form this wraparound 4 minterm implicant. Right. Again, once you do the combination, remember to put down a check mark. All right. And then we're going to check the second element in the first group in column 2. 0, 0 dash 0. And actually, when you do comparison, you will only compare it with some elements over here that have the dash in the same position. If they don't have dash in the same position, again, they definitely differ by at least 2 positions. One on the dash, and the other one is like the dash for the other representation. These two things have to have the same dash positions for them to be adjacent. So that also saves me a lot of comparison work. So I'm looking for a neighbor of 0, 0 dash 0. Right, I'll only check anything with a dash on the third position. So let's say 1, 0 dash 0. They differ on one of the numbers, 0 versus 1. So they can be combined into dash 0 dash 0. Put down a check mark indicating that those 2 minterm implicants are no longer prime. Right. Again, 2 different interpretations through Boolean algebra and Carnot map. So through Boolean algebra, what we're doing is that A prime, B prime, D prime plus A, B prime, D prime gives you B prime, D prime. Right, for the 3, red-colored implicants. In the Carnot map, we have 0, 0 dash 0. So 0, 0 dash 0. That is this top and bottom minterm forming the wraparound implicant. And 1, 0 dash 0, the top and bottom wraparound implicant from the 4th column. And they can be combined into that corner implicant. Right? Dash 0 dash 0, which is B prime, D prime. So this is just to confirm that what we are doing over here in this binary manipulation is actually the same as Boolean algebra and K-map. Right. And then if I do like more, okay, I'm going to draw some lines between these three implicants. All right, so I think there are some more neighbors. Dash 000 can be combined with this one, and also dash 010, this one. Dash 000 has two neighbors in the second column. Right? They have the same dash position, and they differ by one binary bit in the other positions. But as you can see, if you look at column 3, within the first group in column 3, we do have some duplicate elements. We have that dash 00 dash, dash 00 dash appearing twice. Right? Any idea why it's appearing twice? Yes, Eric. Exactly. You can use two pairs of two minterm implicants to construct a four minterm implicants. That four corner implicants can be constructed by merging this column, top and bottom, and last column, top and bottom, into a four minterm implicant. You can also do this combination in a slightly different way by combining this two minterm implicant, the top row, and the the bottom row, left and right two minterm implicants, to create again that very same four minterm corner implicants. So there are two different ways you can construct a four minterm implicants through two different pairs, like two distinct pairs of two minterm implicants. Right. So therefore, in that case, what we can do is we can just keep only a single copy of that implicant in column 3, because they really represent the same implicant. And then don't forget to always put down a check mark whenever some implicant is used for combination to create a bigger one. And this is what we arrive at in column 3. Right. And actually, we are doing a bit more comparison by checking all the elements in column 3 and to see if they can be combined. And the answer is no. They always differ by more than one bit. So that concludes this tabulation method. All right. So at this point, we cannot do this combination any further. So all the minterms, or actually all the implicants that are left behind without a check mark, those are the implicants that cannot be combined with other implicants to grow further. So those are prime implicants. Everything that is not checked off are prime implicants. Right. So these are all the implicants left. And let's just verify again through K-map that indeed they are prime implicants. So 0-01, these two minterms, and that's a prime implicant. You can now grow it to top, right, bottom. It's already fully grown. 01-1, so 01 column, dash 1, these two, which is again a prime implicant. 011 dash, 011 dash, another prime implicant. And these prime implicants appear in column 2, which means they cover two minterms. And that's what we saw in the K-map as well. Dash 00 dash, so B equals 0, C equals 0, B equals 0, C equals 0. And that is this wraparound implicants. B equals 0, C equals 0. And then you have B equals 0, D equals 0, the four corners. And finally, dash dash 10, the bottom row of minterms. Right. And these are indeed what you should get by just working with K-maps. Right? Make sure you can get the same set of implicants from K-maps, but also, with this algorithm, you get the same result. So for this example, it probably doesn't make sense to use the method at this algorithm. It's just too much work. Visually, with the help of K-map, you can easily find out the prime implicants. But think about 10 variable function, 20 variable function. At that point, you no longer have the luxury of using a K-map. So you probably have to resort to this algorithm. Right. And that's really the first step of the Quine-McCluskey algorithm to find all the prime implicants. In K-map, you do visual grouping. In the QM algorithm, you do this tabulation method to do binary grouping right, with the help of the little box to identify prime implicants and also dashes to indicate the disappearance of a variable. All right. Any questions? All right. So if there's no question, we're just going to move on to the second step of the QM algorithm to really find the minimal representation. That's what we did with K-map, to first find prime implicants and then pick essential prime implicants, include them, cover the remaining ones. That process can also be formalized as what is called prime implicant chart in the QM algorithm. All right, so we're going to take a look at that. All right, so given these prime implicants in a K-map, the next thing you will do is to find the essential prime implicants. There are two minterms that are only covered by one implicant, so those implicants must be essential. All right. And the question for us is that how do we check for that through binary and dash representation? Given this set of binary numbers with some dashes and boxes, right, how do we check for that kind of relationship? Well, the binary number by themselves doesn't tell you much about which implicant covers which minterm. So we do need another representation. Right? And this is a classical cover problem. Given a set of implicants and a set of minterms that need to be covered, we can plot them in a table by putting all the implicants over here, all the minterms over there. And for each minterm covered by the implicant, we're going to put down an X mark in the table. Right? So when we see an X mark, that indicates this implicant covers minterm 0, minterm 1, minterm 8, minterm 9. And again, let's just try to verify that really quickly in the K-map. The first implicant, B prime, C prime, B prime, C prime, which are these minterms, these implicants cover minterm 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So indeed, minterm 0, 1, 8, 9, as shown in the table. All right, and we just do that for each and every implicant. So this table is really a flattened out version of K-map. K-map tells you the coverage relationship, which implicant covers which minterm. This table also shows you the same relationship. But what the table doesn't show is adjacency relationship. All the adjacent information is not represented. Minterm is just listed based on that binary sorting, right? Without any adjacency information. So really, the QM algorithm decouples the two steps. One step is the adjacency analysis to find prime implicants. The other step is the coverage analysis to find the best way to cover all the minterms. K-map is a singular representation for both problems. QM decouples them into two different representations. Tabulation method for adjacency analysis, prime implicant chart for coverage analysis. So given this table, what do you think we can do with it? Right? How do we find the minimum way to cover all the minterms? Where do we start? We start with essentiality, same as how we deal with K-map. So essentiality is saying that if a minterm is only covered by one prime implicant, we must include that prime implicant in the final representation. And in this table, it will show up as a column with only a single cross mark. That means that minterm is only covered by a single implicant. And in this case, we have two essential prime implicants because minterm 9, which is 1001, 1001, is only covered by that implicant. And minterm 14, 1110, is only covered by that implicant. So essential primes will show up as a column, like a minterm, only covered by one implicant, and that implicant is said to be essential prime. Right. And once we find the essential prime, well, the way we do it is we put down that these two implicants in my final expression. And then actually I can simplify the table a bit further. All the minterms that are already covered by essential prime implicants, well, if they're covered, they are covered. You don't have to cover them again. Right, so anything that is covered by those two essential prime implicants, all the columns can be essentially ignored because they have already been covered. Right. This is really saying that in the K-map, these mean terms, you don't have to worry about them anymore. I already have those implicants in my expression. With that, we can actually greatly simplify the table. Right? We can cross out all those columns and those two rows, and now we're left with a much smaller table, representing what are the implicants and can cover the remaining ones. And indeed, if you look at this table, at this point, what are left is just this much smaller table, right, telling you how to cover minterm 5 and minterm 7. And minterm 5, 0, 1, 0, 1, and 7, 0, 1, 1, 1, those are the two remaining minterms. With the help of essentiality, we can include some implicants in my expression and then simplify the problem. All right. So within this set of 2 minterms and 3 implicants, any ideas of what we can do to find the best cover? Or you can just tell me what the best cover is. Right? What is the implicant that I need? A prime BD? Yeah, A prime BD. That's indeed what I need. This is that one implicant that can cover both minterms. Right? In terms of K-map, A prime BD is the remaining 2 minterm implicant. So A prime BD is what I need. And again, remember here we're trying to develop an algorithm. Right? And why did you pick A prime BD? Right? Try to articulate a reason based on that prime implicant chart. Right? What is the reason? Yeah, it covers the most remaining minterms. In fact, it covers all the remaining minterms, right? And that's very nice, right? And the other observation would be, well, this minterm just strictly covers more than the other ones, right? This covers 2, which is a superset of the coverage of the other implicant. So in that case, this minterm is just more capable than the other 2. So that idea, the observation is formulated into the second rule that you can apply to prime implicant chart. If there's a row that appears to be bigger than other rows, you can get rid of the smaller rows, since this one provides strictly more coverage than these other implicants. Right? In this example, that covers everything. But in the other example, you could left still with quite a lot of variables. So the main objective is to prune the table further, so that at some point you can apply a greedy algorithm to identify the minimum cover. Right? So the second method of doing table pruning is called row dominance. So one row dominates another row if that row is bigger. In this case, the row A prime BD dominates A prime C prime D, and it dominates the bottom row. And we can eliminate the smaller row. There's just no reason for you to use the smaller row. Anything that the smaller row can do, the bigger row can also do. Right? It's only going to do better. So in that case, there's no need for the smaller row. All right. And if we do this row dominance by getting rid of the smaller rows, and if you look at the remaining prime implicant chart, you sort of have like 2 minterms to be covered, and you only have 1 candidate. At that point, this one sort of becomes essential. Right? You only have like 2 minterms, 1 implicant left, and this one doesn't provide any coverage for the remaining minterms. So this one is really the only way to cover those 2 minterms. At this point, you can actually call this implicant to be essential. You have 2 columns, 2 minterms that can only be covered by that 1 implicant in the pruned table. We have essentiality defined based on the original set of implicants. That is my starting point for pruning the table. And after you have done more table pruning, you can actually identify more relatively essential implicants. Right? And with that, we apply the essentiality to include A prime BD in my final expression. In fact, this algorithm involves essentially 2 stages. Stage number 1 is to do some kind of pruning, some kind of elimination to reduce the table, to simplify the table. And essentiality is the only rule that can be used to add implicants to the final expression. All of the implicants are added only when they are essential. Right? Whether they're essential from the initial state of the table, or they're essential after some pruning and based on this current condition of the table. And with row dominance and essentiality, you can apply them again and again until you have pretty much covered all the minterms. And there's another rule you can apply to the table, which is called column dominance. Again, this duality is really bothering us. You always see pretty much two kinds of things for each topic. And here's the manifestation of duality in this prime implicant chart. Row dominance is saying that you can get rid of the smaller row. Column dominance is saying that you can get rid of a larger column. Right? So for example, let me see how I can apply column domination in this example. Well, I could say, for example, if I look at column 8 and column 9. If I look at these two columns, right, you could apply essentiality. That's definitely one option. But you can also apply some other operations to simplify the table. And in this case, you can get rid of column 8 and just ignore it altogether in the rest of the algorithm. Right, this is a little bit counterintuitive. I think row dominance makes a lot of sense. The one that provides bigger coverage, you keep it. Column dominance, it's a little bit counterintuitive, right? And the reason why we can get rid of this larger column, right, as a step to prune the table is because column 8 is easier to cover than column 9. In fact, any method that covers column 9 will also cover column 8. Any method that covers column 9 will also cover column 8. Column 8 can be covered by two methods. Column 9 can only be covered by one method. And that one method that covers column 9 also covers column 8. So once you get covered column 9 or minterm 9 covered, you don't have to worry about covering minterm 8. And that is true even, let's say suppose I have like more cross marks in those two columns. I have an X over here, I have an X over here. In that situation, you can also get rid of column 8, just because it's easier to cover than column 9. And any method that covers column 9 will also cover column 8. Yes? Column 10, yes, it does. It applies to also, so I say column 10, column 2, and column 6. Because you have a smaller column, column 14, and once you cover 14, those columns will also be covered. In this case, you can sort of see that relationship by applying essentiality, and that is also what you get by applying the row dominance. So we have three rules: essentiality, row dominance, and column dominance. You can apply them in any order you like, and even at some point apply essentiality to include more implicants in your final cover, and that should allow you to find the minimum expression in most situations. And the order of applying these operations doesn't really matter. With any sequence, you will get the same result. Usually, I tend to prefer essentiality and row dominance since they are just visually more pleasing. But definitely keep column dominance in mind, because in some very hard examples, which is really hard to illustrate with less than 10, 20 columns, you need column dominance. So with that said, I'm going to go through another example of prime implicant chart. Again, a much larger chart. So you have to do a lot of visual analysis to figure out which one is essential. And here are all the essential minterms. Minterms are only covered by one implicant, so the corresponding implicant P1, P6, P2, those are essential prime implicants. All right, so I would include those three implicants in my minimal expression to take the sum of those three implicants. And once I do that, these implicants are included, and any minterms covered by these implicants can also be eliminated from the table. So these are the other minterms covered by the 3 essential prime impedance. I can ignore those columns to simplify my table greatly. All right. So at this point, we're looking at a much smaller table with only 6 check marks. You can represent that as a cross mark. You can represent it as check mark. It's up to you. It's really, a cover table. And for those remaining minterms, any ideas of, which of the rules we can apply? Essentiality, row dominance, column dominance. Which one do you think we can apply? You can apply essentiality. Which one do you think is essential? Here's row dominance. Yeah, we cannot quite apply essentiality yet. Right? Every column has 2 check marks, which means every minterm have 2 choices. They can be covered by 2 impedance. But we can apply row dominance at where? Yeah, so P4 covers these 2 minterms, which is greater than the coverage of P3 and P5. So with that, we can get rid of P3 and P5. And you see P7 and P8, they really have the same coverage. So you can say they sort of like row dominate each other, or you can say they're equivalent. Either way, you can get rid of one of them. Right. So P3 and P5 are eliminated because of row dominance. P7 and P8, you keep one of them because they're interchangeable. And now, at this point, you can finally apply essentiality to include more impedance into the final expression. So 5 makes P4 essential. Minterm 1 makes also P4 essential. So we just add P4 and also P8. That's minterm 23, which is a very big number. We have only seen minterm 15 so far, right, in the 4-variable K-map. So this is really a large example. But still, after these iterations of essentiality, row dominance, essentiality, row dominance, we can finally identify the minimal expression with 5 impedance. All right. I think at this scale, this method would be easier than like having a 5-variable K-map. 5-variable K-map is already a big hassle to deal with. All right. Yeah. Any questions about this, the prime impedance chart, the construction or the solving process? All right. So I think maybe you have seen this kind of methods in other classes. Just in general, if you want to solve this cover problem, this is the method. And this is actually the very first method to solve cover problem. Cover problem is a general problem, right? We can say, what is the minimum number of identities to cover all the students in the classroom. Any of these questions, a defined set of categories and a bunch of elements that can be analyzed using a cover problem. And this algorithm is really motivated by digital design. Digital design is the birthplace of the cover problem, the cover algorithm. And this algorithm is used in many other problems. And there are actually quite a few other problems, like other algorithms that are motivated by digital design. Right, 1950s, 60s, 70s, when people are really trying to design big integrated circuits, they need new algorithms, and those algorithms get applied to solve many more problems. All right, so that's about the tabulation method and the prime impedance chart. With that, you can usually find the minimum expression already. And there are 2 missing pieces that we need to answer. Number 1 is about these incompletely specified functions. Right, in a K-map, what you will do is you would again find all the prime impedance, find the essential prime impedance, use them, and then cover all the ones. You just don't have to worry about the coverage on the don't cares. So in this case, I would probably say that for that K-map example, this is an essential prime impedance in this incompletely specified function. This one is another essential prime impedance. Right? And with that, I don't have to worry about the bottom 2 don't cares. So once I've covered all the ones, I'm done with the cover problem. Right? So I get my minimal expression. In the Quine-McCluskey algorithm, we use tabulation method to find prime impedance. Right? To find this prime impedance, I sort of have to include the don't cares. Right? Particularly to find this prime impedance, I need to treat x as a 1. So that can be used for that grouping and uniting part of the algorithm. So really, I can be conservative and treat all of them as ones to get as many prime implicants as possible, right? And then handle this cover problem in the second part of the QM algorithm. So in the tabulation method, we treat all the don't care as ones to find the most number of implicants. And when we're trying to cover them in that cover table, you see we have different columns for different minterms. You don't have to include any of the x's. The don't cares don't have to be covered. So in the implication chart, we treat x as essentially zeros. Do not put them in the columns of the prime implicant chart. And here actually I have a small example so that I can illustrate the idea. So in this example, there will be 3 prime implicants. This is one of my prime implicants. The wraparound is another prime implicant. This yellow one is actually also a prime implicant, even though it doesn't provide any meaningful coverage. But if we treat it as a 1 in the first step of the QM algorithm, right, all of these x's will be treated as 1s, so we'll be able to find all 3 prime implicants. And I know that these are the only candidates that could possibly go into my minimal expression. Right? Just be conservative and find many as big of an implicants as possible. And in the second part of the QM algorithm, when I put them in this prime implicant chart, again, I include all the prime implicants, but I only put down the minterms as columns. Those are the only things that I need to cover. So let's see. So this green one is really my P1. Right, the implicant that covers 2 minterms. The blue one is essentially my P2 in that table. That only covers 1 minterm. Right, and the yellow one is my P3, sort of providing no meaningful coverage. And then probably I can call this one minterm 110, minterm 10. Okay, the table is actually going in a different order. So 011, 110. MA is my minterm 000. Right, I'm only including the minterms in the table. And as you can see, all of them are essential. P1, P2 are both essential. And with essentiality, I can say my function equals P1 plus P2, which is really to say that the function equals y plus x prime z prime. All right, so incomplete specified function is very easy to handle. You'll be conservative when finding prime implicants to find as many prime implicants as possible. But when it comes to a cover problem, we only care about minterms. So only the minterms become columns that seems to be covered in the prime implicant chart. All right, yeah, any questions? All right, so again, Cardinal, McCluskey, and Hamming, they all worked at Bell Labs at some point. And I would say the ideas that they developed are highly correlated to each other. So Hamming distance is this foundational theory, like to analyze binary numbers. Right? Adjacency is manifested as having a Hamming distance of 1. And this Hamming adjacency idea is then applied in this algorithm format by McCluskey, and also in that visualization by Cardinal. And actually, you see the minimization algorithm by Quine is a little bit earlier. By Quine and McCluskey is earlier. By Quine is earlier than the Cardinal map. And that's really because that's, I think, out of necessity. The algorithm is really what we need to minimize circuit in your computer algorithm. And the K-map is just like a little visualization tool for us to really understand what is happening. Right? But we learned that in the opposite way. We learned K-map first because it's easier to understand. It gives you all the visualization of adjacency and coverage in one place. But the algorithm, dealing with a bunch of binary number, which is not ideal for learning purpose, but it's a lot more efficient for computer execution. All right, so really these 3 ideas, Hamming distance, K-map, QM algorithm, it is one holistic idea, right, developed by people that work at the same place. All right. So I said that there are two missing pieces that we still need to address. Number one is about this incompletely specified function. Number two is in certain conditions, the QM algorithm cannot give you a solution, which is very annoying. Like really, the pruning method that we saw from in the prime implicant chart is a greedy algorithm. Right? You're not making any branches, you're not doing any analysis. Always you pick essentiality, you do as much pruning as possible, so it's a greedy algorithm. And as you can imagine, greedy algorithm has its limitations. So in this implicant chart, again, 6 implicants, 6 minterms. You cannot apply essentiality. Every column has 2 marks. You cannot apply row dominance or column dominance, right? Because they're sort of like staggered in this diagonal pattern. So any row, any column, they are not perfectly a subset of another row or column. So you cannot do anything with this table using the greedy algorithm. Right? And that's how this prime implicant chart translates to in a K-map. You have 1, 2, 3, 4, 5, and 6 prime implicants forming this kind of a chain shape. And we actually saw this example when we analyzed one of the Boolean theorems, consensus. Right? For this function, you have 2 covers. Cover number 1 would be these 3 implicants. And you can represent it as one Boolean expression. And you can apply consensus to get essentially the other solution. Oops. Right, with the 3 blue ones, you can also cover the function perfectly. I think it's a bit hard to see. Let me use a different color. The green ones. Right, with the 3 green ones, okay. The 3 yellow ones, you get the perfect cover. The 3 green ones, where everything gets shifted by 1 position, you get another perfect cover. And both of them are equally minimal. Right? You cannot do any pruning in the prime implicant chart. Then that's a problem we need to address. We want the algorithm to be able to handle any functions. And this condition is actually called a cyclic function or cyclic core. This could be your full function, or this could be what you're left with once you have applied all those pruning methods. Row, column dominance, essentiality, you have already pruned away all the other rows and columns, and this is what you're left with. Right? So this is called a cyclic core or cyclic function. There's a cyclicity dependency that cannot be resolved using a greedy algorithm. So to solve this problem, we essentially apply a formal method. And this formal method works as follows. I'm going to represent this problem as a circuit. Right? Forget about the original circuit. I need to implement this really a circuit model of a new problem. And I'm going to represent each product term as one new variable. And when that variable is 0, that means I do not include the product in my expression. When the variable is 1, that will indicate that I'm including I'm including the product in my expression. So if you look at this equation on the left, right, that's a new equation based on these newly defined variables. And this is saying that in order for me to cover all the minterms, I need to use either implicant 1 or implicant 2 to cover the first minterm, right? Or I need to use implicant 1 or implicant 3 to cover minterm 1, and I need to use implicant 2 or 4, right? One of them to cover minterm 2. Every column gets translated into an equation, and all of them will be ANDed together, right, to indicate that I need to cover minterm 0 and minterm 1 and minterm 2 and minterm 5 and 6 and 7. All of them need to be covered, so that gets translated into a product of sum expression. And for any assignment to these 6 new p variables that make this equation or this expression evaluate to 1, that's one way of covering all the minterms. So for example, if I assign, let's say, p1 to 1, p4 to 1, and p5 to 1, this equation will evaluate to 1. Because I can cover all the minterms using p1, and P4, and P5. Right, those three implicants provide me with one minimal cover of the function. And if I plug in those values into the expression, right, this is a 1, P1 is a 1, P4 is a 1, P5 is a 1. So each clause, each sum term has one of the variables being 1. So therefore, that overall expression will evaluate to 1. And this assignment is what I'm trying to solve from the equation. I'm trying to find a way to set the fewest products, the fewest p variables to 1, so that that expression evaluates to 1. By fewest, that essentially means I'm including as few implicants as possible to cover all the minterms. Right, so I'm trying to find an assignment to these variables with the minimum number of 1s to those p variables so that the expression evaluates to 1. And this is really the problem called Boolean satisfiability. Boolean satisfiability is a very widely used tool. And SAT is one of the first problems that is proven to be NP-complete, I guess. And this has a lot of applications more than just minimizing logic circuit. You can use SAT as a formal tool, a formal solver, to handle many problems. By modeling your problem as a bunch of Boolean variables, and then model the problem as a circuit, and finally, find a way to assign some value to the circuit inputs to produce a 1 at the output. And so the SAT problem is really, given a circuit, what is the set of input values that give you a 1 at the output? For this product of some circuit, well, to have a 1 over here, you need to have 1s in all of the gate inputs. Right? You can probably solve it by running simulation, essentially plugging some values into the circuit, or analyzing the behavior of the gates going backwards. Right? Or you can put this in a K-map and then find some input values that produce a 1 at the output. That's essentially the solving process for a Boolean satisfiability problem. But it's actually quite difficult for this example. To have 1s here, you need to make sure that one of the inputs to this OR gate, for each of these OR gates, has a 1. Right? 1 here, 1 here, 1 here, 1 here. And these OR gates share the same inputs, so there's going to be some conflicts, right? Particularly with some of these inverters, you're going to get some conflicts. So you have to be quite careful when finding the valid input assignments to produce a 1 at the circuit output. Right, it's doable. It takes well, for this function, you can put that in a K-map, so it's not too complicated. But think about 1,000 or even 1,000,000 variables. That's the scale of SAT problems in real life. It's almost impossible to solve it in this kind of circuit format. If you can model your problem as a sum of product circuit, and you're trying to find out an input assignment that gives you a 1 at the output, what you can do is, well, to have a 1, one of these have to be a 1. Right? So I can just set this to be a 1, and then go back through this AND gate, set both of them to be 1, and then I immediately get my solution. For an SOP circuit, if you're trying to find a condition producing a 1, you essentially only have to analyze one of the AND gates. Right? Just make it a 1. And that always works, because you don't have to worry about its correlation with the other gates. So I'm saying that solving for a 1 output from an SOP circuit is trivial. Solving for a 1 from a POS circuit is very difficult. And remember how we modeled our problem earlier? As a product of some expression, which means solving for the solution like this, right? 3 variables equal 1, producing a 1 from the expression. It's a quite difficult job. But you see, we have seen Boolean algebra. You can do conversion between POS to SOP by applying distributivity, right? Or applying some of the other Boolean theorems. But we know SAT is an NP-complete problem. And solving SAT over there is very easy. So this conversion process must be very difficult. Right? Indeed, applying distributivity is very difficult. It just takes a lot of brute force. If you have thousands of different products, thousands of different sums multiplied together, you have to do all the combinations, which is a huge amount of work. And in general, indeed, converting between POS to SOP is difficult. So in real life, people solve SAT problem by developing some heuristics from this kind of representation. Unit propagation, purification, term elimination. they can sort of do a branch and bound method to solve the problem directly from a POS circuit. But we're not worrying about any of those. We're coming back to this expression and then just try to solve it in a brute force method to find the solution. And that's all we're trying to do in this class. To solve it, you can convert this into an SOP by applying a bunch of distributivity to that original formula. And from here, right, in this sum or product expression, finding an assignment that produces a 1 is trivial. Just assign this 4 to 1, you get an output of 1. Right? Or assigning this 3 to 1, you get an output of 1. Finding that assignment producing a true value at the circuit output is trivial. But in terms of logic minimization, you see each variable represents the inclusion or the exclusion of one of the product terms in the final expression. And you want to find the minimal expression with the fewest products. So among all these different ways of producing a 1 at the circuit output, we're going to look for the one that involves the fewest variables. And that is the minimum number of products that you need to cover all the ones. In this example, you can use P145. That's one of the product term in the formula, right? Or 236, another product term with the fewest number of variables. And those are the minimal way to cover the function. So again, 1, 4, 5. They cover all the columns, essentially cover all the minterms. Or alternatively, you can use 2, 3, and 6. Again, a different way to cover all the minterms. I get to find that by modeling this condition that needs to be satisfied, right? Cover M0, cover M1, cover M2, cover M5, M6, M7, and then convert that into an SOP, and then find out these products with the fewest variables to represent the minimal way to cover the function. Right. And starting from there, we simply need to combine them, pick these prime implicants, put them into my SOP expressions. Right? So each implicant goes into my SOP expression. So I have 2 minimal SOP implementation of that circuit. Any questions? All right. So that's the end of today's lecture. We talked about the Quine-McCluskey algorithm. First, finding prime implicants using the tabulation method, and secondly, solve for the cover problem to cover all the minterm with the fewest number of implicants using the prime implicant chart. And in that kind of cyclic dependency, when we cannot prune the table any further with the greedy Quine-McCluskey algorithm, we can apply Petrick's method to solve it formally. Model it as a satisfiability problem, do this SOP, POS conversion for us to easily identify the minimal expression, the minimal solution. So again, the midterm grade is already out. I'm going to talk more about it tomorrow when the survey is also due, so I get to see some of your responses. All right.
Can I say something cool?
Huh?
Can I say something cool?
Yeah. That's very realistic.
I don't know.
Oh, let me double check.
But whatever. So they
Okay. Way better. What's way better mean?
like minor mistakes. Whatever.
Oh, is this you?
Yeah.
Oh, sorry. I didn't recognize it. Yeah, I probably accidentally. I'm going to activate your account. Check again to see if it works. Yeah.
Do you think my midterm's good enough for you for me to do research?
I think you did very well. Even though I always hope people can do better.
But minor mistakes all the way.
Yeah. I mean, it's not a bad score.
Oh yeah.
It's really not bad. It's pretty good.
What's the average?
Like 111.
Really? That high?
Yeah.
God. But mine's okay. It's a little.
Yeah.
What's the highest score? Did someone score 100?
150.
Yeah. So there's like a 10-point curve. So someone got pretty much near perfect.
Okay.
Yeah.
Depending on how my final do, can you refer me?
Yeah. Of course.
Okay.
Yeah.
Alright, cool.
Yeah. Try to do better in the final.
Alright.
Alright.
When you get like 140.
A little lower. Yeah, kind of lower.
Yeah, the TA will have the discussion. I think he will go over the exam questions, right?